Hi all, welcome to MACM 101 tutorial 12. Today we are covering integers and it would include calculating HCF, LCM, inverse using extended Euclidean algorithm, and Chinese remainder theorem. This video is the last of the tutorial series for this term. So I would like to wish you all the very best for the finals. Feel free to reach out to us if you need any help with any of the concepts. So let's get started with the tutorial. Now the first question is for positive integers a and b. We are given that d is the greatest common divisor of a and b. So we have to prove GCD of a by d and b by d is 1. So since d divides a and b, we can write that a is d times a1, a1 being some integer, and b is d times b1, and b1 is some other integer. Now let e be the GCD of a1 and b1. So since e divides a1, we can deduce that d times e would divide d times a1. So here we are just multiplying d on both sides. And d times a1 was a. So de will also divide a. We can do the same thing for b as well. So since e divides b1, d times e would divide d times b1, and d times b1 was b. So de divides b as well. Now here we use the definition of GCD, and we would say that d times e is equal to d itself. Now this is because since d was the greatest common divisor, d times something cannot technically divide a and b unless that something was 1 itself. So here we say that e is equal to 1. And since 1 would divide a1 and b1, the equality of e being the GCD of a1 and b1 is also true. So GCD of a by d and b by d is equal to GCD of a1 and b1, which is 1. Moving on to the second question, we have let n be a positive integer and prove GCD of n and n plus 2 is equal to either 1 or 2. Now it depends upon what's n, whether n is odd or if it's even. So for the first case, if n is odd, let n be 2k plus 1 for some integer k. And n plus 2 would be equal to 2k plus 3. And the GCD of n and n plus 2 is equal to GCD of 2k plus 1 and 2k plus 3. Now this can be rewritten as GCD of 2k plus 1 and 2k plus 3 minus 2k plus 1. Now this comes from the Euclidean algorithm itself. If you remember, we write one number as a linear combination of the other number plus a remainder. And then we shift those remainders by one place and do the same calculation again in the Euclidean algorithm. So that's what we are doing here. So GCD of 2k plus 1 and 2. Here 2k plus 1 is odd while 2 is even. Therefore the GCD is 1. And in the other case, if n is even, n can be rewritten as 2k for some integer k, and n plus 2 would be equal to 2k plus 2. So the GCD of n and n plus 2 is the same thing as GCD of 2k and 2k plus 2. Using the same Euclidean algorithm, this is equal to GCD of 2k and 2k plus 2 minus 2k, which is GCD of 2k and 2. Now since 2k and 2, they are both even, that means 2 can be a common divisor, and it would be the largest common divisor, as GCD of two numbers cannot be greater than the smallest of those two. So if your numbers are 2 and 2k, your GCD cannot be greater than 2. So therefore, the GCD of n and n plus 2 is 2 if n is even, and is 1 if n is odd. Moving on to the third question, we have find the greatest common divisor of 168 and 456, and also the numbers u and v, such that GCD of these two numbers is equal to 168u plus 456v. Now we use the extended Euclidean algorithm here. So first we'll write 456 as a linear combination of 168 and with a remainder. So 456 is 168 times 2 plus 120. Now you rewrite 168 as combination of 120 with a remainder, and you keep on shifting them left until and unless you reach 0. So R2, which is 120, is equal to R3 48 times 2 plus 24. And 48 is 24 times 2 plus 0. Now since we have a 0, which is R5, so your previous remainder would be the GCD. So GCD of RK and 0 is RK. Here the GCD would be 24. So GCD of 456 and 168 is 24. Now to find u and v, we start from the last equation and traverse backwards. You would write R4 as a combination of R2 and R3, and you go up until you reach R1 and R0. So from equation 3 here, the first equation was 456 is 168 times 2 plus 120. Second equation was 168 is 120 times 1 plus 48. And the third one is 120 equals 48 times 2 plus 24. Now here, I'll just move 48 times 2 on the other side, and that will give me 24 as a combination of these, R2 and R3. So 24 is 120 plus 48 times minus 2. Now you have to take care of what number is your remainder and what is the coefficient of that. We don't want you to solve these equations. Now from equation 2, we rewrite 48 as a linear combination of 168 and 120. Now we simplify this. So this would be 120 times 1 plus 120 times 2 from the second part. So this is 120 times 3 plus 168 times minus 2. Now we have R1, all we need is R0. So we rewrite R2 as a linear combination of R0 and R1. So this gives us 456 times 3 plus 168 times minus 8. So your U is minus 8 and your V is 3. And that's all we have to find. So this is the extended Euclidean algorithm. Moving on to the next, we have to find the greatest common divisor and the least common multiple of 630 and 40,452. Now this is a fairly simple problem. This is just done by the Euclidean algorithm. You write 40452 as a combination of 630 and a remainder. And 630 is equal to remainder times 4 plus another remainder. And then you again move the first remainder to the left side. So 102 is 30 times 3 plus 12. 30 equals 12 times 2 plus 6. And 12 is 6 times 2 plus 0. Now, since we are at the remainder equals 0, the previous remainder would be our GCD. So GCD of 40452 and 630 is 6. Now to find the LCM, we have two methods. One is what we learned in high school, straightforward, just use prime factorization. So write each number as a combination of prime numbers and find out which numbers are common, write them only once, and write rest of the numbers as it is, and that would give you the LCM. So 40452 is 2 times 2 times 3 times 3371, and 630 is 2 times 3 times 3 times 5 times 7. So we write the second 2 only once and the 3 and 1 3 only once. I missed another 3 here, so this would be multiplied by 3. Now another way to find the LCM is if you already have your GCD available. So LCM is the product of two numbers divided by the GCD of those two numbers. So 40452 multiplied by 630 divided by 6 is the same as what we found using prime factorization. For the fifth question, we have to find the prime factorization of the given three numbers. So the easiest way which I like to use is create a table. On the left hand side, write down the number which you are dividing it by. So start with 2, then move on to 3, and then move on to the next highest prime, which is 5, and then 7 and 11, and so on. So dividing 148500 first by 2, then whatever the answer is. Again, start with 2. Then for 3, to check the divisibility for 3, you just sum the digits of the number. If the sum is divisible by 3, the number is divisible by 3. And in the same way, we move on till the end, unless we either get a prime number, so which is 11 here, and that's the prime factorization. It is 2 square times 3 cube times 5 cube times 11. So the process is same for the other two questions as well. You just start dividing by 2 and then try with 3, then 5, 7, and 11, so on. Now moving on to the sixth question, we have how many positive divisors are there for n equals 2 to the power 14, 3 to the power 9, 5 to the power 8, so on. So how do you find a divisor? Now, since we are already given the prime factorization of n, any combination of these numbers would be a divisor. So if you just take 2 to the power 14, it will divide the whole thing. If you take 3 to the power 9, 5 to the power 8, 7 to the power 10, it's also a divisor. Just 3 to the power 8 will be a divisor as well. So any possible combination of these numbers would be a divisor. So when n is equal to p1 to the power i1, p2 to the power i2, so on till pn to the power in, with p1, p2, p3, so on till pn being distinct prime numbers, then p1 to the power j1, p2 to the power j2, so on till pn to the power jn is a divisor of n for all j between 0 to I. And this would be for j1, j2, j3, everything till jn. Now, since jk is between 0 and ik, inclusive of 0 as well. So there are I k plus 1 possible values for j. So if your I was, let's say, 5, that means 0, 1, 2, 3, 4, 5. That means 6 possible values for jk. So the number of possible values for p1, j1, p2, j2, so on till pn, jn would be I1 plus 1 times I2 plus 1, so on till in plus 1. Now this is by the rule of product, because you could keep 2 to the power 14 constant and then move to 3 to the power 9, or the first two prime numbers constant, move the rest of the numbers. So that's why we are doing a multiplication here. It would be 14 plus 1 times 9 plus 1 times 8 plus 1 times 10 plus 1, 3 plus 1, 5 plus 1, and again 10 plus 1. So the total possible divisors are 3,920,400. Moving on to question 7. A perfect square is a number n such that n is equal to k square for some integer k. Determine the smallest perfect square that is divisible by 7 factorial. Now, to have a perfect square, you should know that if you were to write down its uh, prime factorization, every prime in the factorization would have an even power. So first just write down the prime factorization of 7 factorial, which is 2 to power 4 times 3 to power 2 times 5 to power 1 and 7 to power 1. Notice that 5 and 7 are the only numbers with odd power. So if we were to multiply it by 5 and 7, it would become a perfect square and would still be divisible by 7 factorial. So we multiply by 35. So it is 2 to power 4 times 3 square times 5 square times 7 square. Now this is a perfect square and is still divisible by 7 factorial because it's coming from its prime factorization. For 8th question, we have find the inverse of 5 mod 13 and 22 mod 27. Now, one thing to just note here is that inverse of A mod B will exist as long as GCD of A and B is 1. So to find the inverses, we will use the extended Euclidean algorithm. So first we'll find the HCF. If the HCF is 1, we'll move on to the next steps. For finding the inverse of 5 mod 13, we'll write 13 as a combination of 5 with a remainder. So 13 is 5 times 2, which is 10, plus 3. Now 5 in terms of 3 would be 3 times 1 plus 2, and 3 is 2 times 1 plus 1. Now since the HCF is 1 now, we move on to the extended step, which is rewriting 1 in terms of 2 and 3. It would be 3 minus 2, and then 2 in terms of 5 and 3, which is 5 minus 3. Rewrite it as 3 times 2 minus 5, and in the end rewrite 3 in terms of 13 and 5. Now this would give us 13 times 2 plus 5 times minus 5. So the second part is what we are interested in, which is the coefficient of 5. So this is ideally the inverse, but sometimes we do get negative numbers in the inverse. So in order to make this negative number positive, we use the congruence mod n to obtain the canonical inverse, which is just a fancy way of saying 13 minus 5, which is 8. So minus 5 is congruent to 8 mod 13. So the inverse of 5 mod 13 is 8 mod 13. For the second part, we have 22 mod 27. Again, you write 27 in terms of 22, which would be 27 is 22 times 1 plus 5. 22 would be 5 times 4, 20 plus 2. 5 is 2 times 2 plus 1. Again, the remainder is 1. That property holds true. Now we again start to write 1 in terms of 5 and 2. And now 2 in terms of 22 and 5. Rewrite it, which would be 5 times 9 minus 22 times 2. And now 5 in terms of 27 and 22. This would give you 27 times 9 plus 22 times minus 11. Now again, we are only interested in the coefficient of 22, which is again negative. So we will have to find the canonical inverse of this. Again, this would be 27 minus 11, which is 16. So minus 11 is congruent to 16 mod 27. Therefore, the inverse of 22 mod 27 is 16 mod 27. For the last question, we have solve the following system of linear congruences. X is congruent to 2 mod 11 and X is also congruent to 1 mod 7. Now here we use the Chinese remainder theorem as discussed by Professor Bulatov. We rewrite X as a sum of two numbers, which is x1 plus x2. So x1 is congruent to 2 mod 11 and 0 mod 7. And x2 is congruent to 0 mod 11 and 1 mod 7. And since x is sum of x1 plus x2, it will be congruent to 2 mod 11, which is 2 plus 0, or it will also be congruent to 1 mod 7, which is 0 plus 1. Now, we'll solve for x1 and x2 separately and then add them up to get x. Now for x1, since it is 0 mod 7, that means it's a multiple of 7. So x1 can be rewritten as 7 times another integer, let's say z1. Now 7 times z1 is congruent to 2 mod 11. So we'll just do a hit and try here. We'll put z1 as 1, doesn't give us an answer, z1 as 2, so on, until we hit z1 equals 5. So 7 times 5 is 35, and mod 11 would give us the remainder 2. And for x2, we have, since it's a multiple of 11, we rewrite it as 11 times z2, which is congruent to 1 mod 7. Now since 11 is greater than 7, we take the residual here and we get 4 times z2, which is congruent to 1 mod 7. Again, solving it gives us z2 equals 2. So you just try it out with 1, 2, 3, and so on. So x1 is 7 times 5, which is 35, and x2 is 11 times 2, which is 22. So our x comes out to be 57. Now to check it, 57 mod 11 gives us 2 as the remainder. So it solves the first equation. And 57 mod 7 gives us 1, which solves the second equation. So that is it for this tutorial video. If you do have any questions, you can leave them in the Canvas discussion board or join us in the upcoming session if you need help with any of today's concepts or you want to revise the previous ones as well.